Hi, I'm Raunak Jain. Raunak Jain and I are working on this project Sparse Oblique Decision Trees. We are working under Professor Rahul Garg and Professor Ravi. I'll first cover the idea and the intuition behind sparse oblique decision trees. I'll then talk about how example weights are propagated down the tree. I'll then talk about how the predictions of every node are combined together to form the prediction of the entire tree. I'll then talk about the loss function, how the loss function is used for training. I'll then talk about future improvement and the scope for this project. Sparse oblique decision tree consists of multiple nodes. Every node is associated with a weight vector W. The weight vector W is cross multiplied with a data sample X. It is then passed on to an activation function g of x that maps to a real value between -1 and 1. Ideally, we want it to be tan h, or we want to construct a piecewise linear function. If g of xw is close to 1, node 2 is assigned a very high weight g2. If g of xw is close to -1, node 1 is assigned a very high weight g1. The formulas of g1 and g2 are written here. We can see that if y, which is g of xw, is close to -1, then g1 is very high, and otherwise g2 is very high. We know that the sum of g1 and g2 is 1. g1 and g2 are used to say which node out of node 1 and node 2 would be used to predict the example x. If node 1 and node 2 are not leaf nodes, if there are subtrees of node 1 and node 2, then g1 and g2 denote which subtree out of these two would be used for classifying the data sample x. This is a 7-node sparse oblique decision tree. In the 7-node sparse oblique decision tree, we calculate the example weight at node 3, which is z3. Now z3 is calculated using z1. What happens is that z1 is multiplied with z3 hat. z3 hat is 1 minus y1 by 2. z3 hat uses the same formula that we used here for z1, that is 1 minus y by 2. Using the same formula and multiplying it with z1, we get z3. This means that here the weight z at any node is the product of the z hats in the path from the root to that node. z3 is the product of z1 hat and z3 hat. We now talk about the prediction given by the entire tree. At the root node, the prediction given by the tree is z1 multiplied by y1 plus g2 multiplied by y2, where g1 and g2 are the example weights associated with node 1 and node 2. This is done in order to weigh the predictions given by node 1 and node 2 appropriately. The same formula is recursively used at every internal node. For example, at node 1, if it is an internal node, the same formula for the prediction by node 1 would be used there. We now talk about the prediction by a leaf node. The prediction by a leaf node is simply y equals g of xw. We now see the loss function. The total loss function of the entire tree is the sum of the losses at every leaf node. The loss at a certain leaf node is defined in this way. It is defined as a summation over all the examples u of minus gu by u g of uw. Now g of uw is the prediction made by the leaf node. It is multiplied with the actual label yu of the example u, which is then multiplied by the example weight ZU of the particular example U at the certain leaf node. Now this is the loss function that is at a certain leaf node. To get the total loss of the entire tree, we sum over L over all the leaf nodes. In order to train the sparse application tree, the example weights are propagated down the tree. This is done in the manner that is showed here. Z3, Z1 is calculated using Y. Then G3 is calculated using Z1 and Y1. This way, this thing continues until we reach the leaf node. Then, Adam algorithm is used for training every node on the basis of the propagated example weights. We can see that in the loss function here, the propagated example weights ZU are used. The example weights are then re-updated based on the new weights of every node. There have been a lot of new improvements that we have already implemented. For example, we dynamically split leaf nodes which have large number of misclassifications. We split leaf nodes based on the maximum reduction in error rates. We prune the tree to remove the nodes that do not help in classification. There are some things that we plan to do, we have not done them yet. We freeze parent nodes when the misclassification rate is low. We plan to parallelize the training of different nodes. We plan to modify the formulae to do multi-class classification. The underlying idea would be the same. We would just use a different formulation for the leaf nodes. Thanks for hearing this out.